Welcome back to the booth. I'm joined now by Alasdair Allan, Senior Research Fellow at the University of Exeter. Alasdair, thank you very much for joining us.
Hey there, Matt.
So how has astronomy transformed from data poor to data rich?
Well, like everything we do, it's the internet. The internet has done us in. When I started off, and I'm not that old. We were just in the end of the era of large photographic plates, and you took your photographic plate on the back end of the telescope, you exposed it, you had a big stack, you went off, you processed them. You had a photo scanner and a blink comparator, and there was a whole infrastructure build-up of like centuries of work to build this infrastructure.
Right.
And then from, the early 90s till now, we've had to rebuild the whole thing in 20 years. CCD cameras changed everything. We now have, the data coming off the telescopes. And in the last 5-10 years, probably more like 5 years, it's not that the data is coming off the telescopes and it's coming home with you in big tapes. The data is being analyzed in real time at the telescopes.
Yeah.
And you're getting into real minute-to-minute decision-making. I mean, with hardware that costs anything between $1 a second to $100 a second to run.
Yeah.
In the old days, you were slightly more relaxed about it because, there wasn't a lot you could do. And now you can actually see your results coming in real time while you're sitting at the mountain at 15,000 feet, where your decision-making capabilities are, subpar, let's say.
Sure.
And you have to make decisions.
So it speeds everything up.
Yeah, it speeds everything up. It's the thing that everyone else is facing. The decision-making process is much shorter. The amount of data you have to make decisions is so much larger, which is a good thing because you have data to make your decisions on. Evidence-based decision-making, that's a good thing.
Yeah.
But it's also there's so much data you can't make a decision optimally anymore.
Right. So can you talk a little bit about how your telescope network works?
So what I was saying about the optimal decision making, that's how it works. So effectively what I've got is I've got a meta network. So I don't actually have any telescopes of my own. I've got a whole bunch of other people have built some really amazing hardwares, like fully automatic, fully autonomous telescopes sitting on top of various mountains. The LCO GT guys, for instance, the Monet project out of Germany, Raptor Talons out of Los Alamos, a whole bunch of guys. And my software basically embeds smart software at the telescopes. So you've got a collaborative agent paradigm for the CompSci people in the audience. So you've got smart software trying to pursue science goals, trying to get the user's science done. And you've got smart software at the telescopes, but also databases, because if you look at a database and look at a telescope is just a database where you can only retrieve data from the future, and really slowly.
Right.
So basically you've got smart bits of software trying to fulfill data requests. And there's a whole bunch of negotiation that goes on in real time as data requests are made and data comes off the telescope, it's analyzed, and result packets goes back to the agents doing science. And negotiation goes on, and observations jump from telescope to telescope, follows like the day-night cycle of the Earth. It follows the different equipment is on different telescopes. So some requests go to one telescope, some can be fulfilled by another. So it's like a whole real-time optimization thing to achieve science, basically.
Right. Now, does that have application elsewhere? I mean, can you see how it could be used in business or other
Sure.
domains?
And if you come to my talk tomorrow, I have a whole section on this, right?
Nice.
But,
very nice. I like what you did there.
It's good, isn't it? There's basically the architectures I'm using. I mean, effectively, just think of telescopes as really large sensors facing upwards. Right? They're just big sensors.
Right.
So what I have effectively built is a distributed sensor network. Right. So if you think about UAVs or any sort of distributed sensor network, for instance, I'm talking to a couple of people in the UK about North Atlantic buoy networks. So there's a whole network of buoys. I didn't know about this, but apparently there's a whole network of buoys in the North Atlantic to do wind and current measurements.
Okay.
And they're just free-floating platforms, and there's actually tethered platforms, but there's also free-floating stuff. And it's really cool. It's this huge distributed sensor network. But effectively the architectures I built are for optimizing the use of a scarce resource, right? And the scarce resource here is actually power.
Right.
I mean, you'd think something floating in the middle of like big North Atlantic waves, solar, but the power is actually quite short, is in short supply. So you've actually got to you've got to do low level monitoring and then turn on the really high drain sensors when you think it's a good idea to do that. Right? So you can actually have sensors in one side triggering sensor platforms on the other side of the Atlantic, so you're basically going, guys, there's something interesting happening here, it's coming your way, you should turn on and do high rate data monitoring now to get the interesting stuff coming along. So it's like adaptive meshes. Basically it's an adaptive mesh, right? So you're not really taking many sensor measurements when nothing interesting has happened, and then you fire it up and take really heavy duty stuff when interesting stuff comes along. And that's all about negotiation and notifications and all that sort of stuff. So same architectures, different platform.
So last question for you, and it dovetails a little bit with that. For people who are thinking about creating their own distributed sensor networks, what are the things they need to consider from the get-go? I mean, even as you're talking right there, understanding the context of the resources at play, right?
The real big takeaway is the real world is not a computer. Things fail. Things fail badly. The things you made redundant so they won't fail, something else will fail, that means that fails too.
Sure.
Right? So I think for the last 10 years, I've pretty much been working this for 10 years, and the last 10 years has entirely convinced me that in the real world, hierarchical architectures do not work.
Really?
Right. Because something in the hierarchy will fail and it will take out the whole low level of an entire part of your tree.
Right, makes sense.
So for distributed sensor networks, I would really push a peer-to-peer, very flat architecture. And if you have to have a master, then you got to have a redundant master, right? Every node in your architecture has to be able to become that master if it's suddenly, well, I can't hear from anyone else. I'm in charge now.
Yep.
So I think the big architectural takeaway for me is that peer-to-peer is the way to go for sensor networks.
Well, thanks so much for being with us. Appreciate it.
Thanks for having me.